A warm welcome to the 35th session of the second module in the course Signals and Systems. We have been looking at duality in the previous session, and duality was a very interesting property where you derived one principle in detail and you got one principle free. So, in fact, I would like to make this remark a little more explicitly here. So, what is duality? Learn one and get one free is duality. This is the beauty of electrical engineering. In fact, I wanted to mention to you that this is only one instance of duality in the domain of electrical engineering. We encounter duality in other contexts in electrical engineering as well. For example, we encounter it in graph theory, in network theory. We also encounter it in Boolean algebra. So, duality is a very interesting general philosophy where you have an interchangeable situation. You have situation A being analogous to situation B, and with a little bit of change situation B can be modified to become analogous to a version of situation A, and that makes your learning easy. We have seen to some extent how it does it in the previous session in the context of the Fourier transform, but now we look at it in more detail in the same context of the Fourier transform. We will see a much more serious consequence. Last time, of course, we saw a consequence in terms of multiplication convolution parallel. Now we will see a consequence, again multiplication convolution, but taken the other way. So, what we had derived was that if I have x1t convolved with x2t, x1t of the Fourier transform capital X1 omega and x2t of the Fourier transform capital X2 omega, then x1t convolved with x2t has the Fourier transform capital X1 omega into capital X2 omega, provided all these Fourier transforms exist. Now, this is just highly potent as a situation to apply duality. So, suppose I reverse, I apply duality on each of them individually. So, I take as a consequence of duality capital X1 of t having the Fourier transform 2 pi small x1 minus omega, and capital X2 t the Fourier transform 2 pi small x2 minus omega. Then it should be true that capital X1 t times capital X2 t, we can ask what is its Fourier transform. Now, you know, from the last point here we already know the answer. It has to do with x1 convolved with x2. So, let us write that down. So, take the last expression that you had here, use duality on this, and I will write it on the next page. Capital X1t, capital X2 should have the Fourier transform small x1 convolved with small x2 evaluated at minus omega, and of course multiplied by 2 pi. Now, we need to figure out what is small x1 convolved with small x2 evaluated at minus omega in terms of x1 and x2, each evaluated again at minus omega. So, let us now write down this expression. We want to find out x1 convolved with x2 evaluated at minus omega. So, in fact, we will come to a general question here. Let me take x1t convolved with x2t first and replace t by omega as we should be doing here. So, that is x1 lambda times x2 capital omega minus lambda d lambda, and suppose you were to convolve x1 minus omega with x2 minus omega, what would it give you? It would be essentially x1 minus lambda Well, x2, now you need to evaluate at omega, all right. So, x2 omega, you have, so let us put, so if we get confused here, let us put x2 minus omega equal to x3 omega. So, we should write x3 here first, let us do that. So, instead of x2 let us write x3 and then we will write x2. So, x3 omega minus lambda d lambda, and now we will substitute by x2. So, x3 omega minus lambda is x2 lambda minus omega. Now, let us do the trick of replacing minus omega by some other variable. So, let us write this down clearly first. x1 minus omega convolved with x2 minus omega is essentially integral as shown here. So, x1 minus omega, I am repeating here, x1 minus omega convolved with x2 minus omega is essentially an integral x1 minus lambda x2 lambda minus omega d lambda. Put minus lambda is some alpha. So, of course, as usual minus d lambda is d alpha. When lambda goes from minus to plus infinity, alpha goes from plus to minus infinity. But then absorbing the minus sign in minus d lambda, we have x1 minus omega convolved with x2 minus omega is essentially integral minus to plus infinity x1 alpha x2 minus omega minus alpha d alpha, which is essentially x1 convolved with x2 evaluated at minus omega. So, as you see, if I have x1 convolved with x2 and now if I replace that with x1 with its independent variable reflected, so omega replaced by minus omega. Similarly for x2, then in the convolution the same thing happens. You could think of it in time, for example. What we are saying is, if I have x1t convolved with x2t and if I replace t by minus t in each of x1 and x2, what does replacement of t by minus t mean? It means reflection about the point t equal to 0. So, you have t equal to 0, you have reflected, mirrored around that. It is as if you have reversed the order of time. You are going from time t equal to plus infinity towards t equal to minus infinity. If you do it for x1 and if you also do it for x2, you are also doing it for the convolution. That is what we have written here. So, essentially what you have is that x1 of minus omega convolved with x2 of minus omega is indeed x1 convolved with x2, which would have normally evaluated with again its independent variable time reversed. Now, we have a very interesting conclusion that we can draw. Let us draw that conclusion. So, what we have seen so far is that capital X1 of t has the Fourier transform 2 pi small x1 minus omega, and capital X2 of t has the Fourier transform 2 pi small x2 evaluated minus omega. Now, what would be the Fourier transform of capital X1 t into capital X2 t? If we go by duality, we have shown it to be 2 pi x1 convolved with x2 evaluated at minus omega. But x1 convolved with x2 evaluated at minus omega is what we have just shown to be x1 at minus omega convolved with x2 at minus omega. So, you could multiply both sides by 2 pi. So, I have 2 pi times x1 convolved with x2 evaluated at minus omega is, now you will wonder why I am doing this, but you will understand in a minute. I will say 1 by 2 pi times 2 pi x1 convolved with x1 at minus omega, of course, convolved with 2 pi x2 at minus omega. Now, here I am using the property that if I multiply any of the functions by a constant, the convolution also gets multiplied by the same constant. So, if I look at this expression, I am multiplying x1 by 2 pi and x2 by 2 pi, and therefore, I have also divided by 2 pi. So, I have only one 2 pi left, which I have on the other side. So, one 2 pi here, there are two 2 pi's here, but I have cancelled one of them by division. I am doing that intentionally, because now you can identify something very interesting. This is essentially this. I am showing them in different colors, and this is essentially this. And what we are saying here is that we are convolving this with this, the red with the green, and then dividing by 2 pi. So, the conclusion we have drawn is that when I multiply two functions, their Fourier transforms are convolved and then divided by 2 pi if I am talking about the angular frequency domain. So, if I have expressed the Fourier transform in the angular frequency domain, I have a very simple and a beautiful expression for the Fourier transform of the product of two functions, and that is the convolution of the corresponding Fourier transforms divided by 2 pi when expressed in terms of angular frequency. This is a profound conclusion. Let me again emphasize this based on what we have just written down. So, let us look at this again. What I am saying is, here I have x1t, I am underlying the relevant things. x1t has the Fourier transform 2 pi small x1 minus omega. Capital X2t has the Fourier transform 2 pi small x2 minus omega, and we have seen that capital X1t into capital X2t essentially has the Fourier transform 1 by 2 pi, the Fourier transform of capital X1t convolved with the Fourier transform of capital X2t. So, multiplication of time functions results in convolution of their Fourier transforms. That is what we are saying. Let us now make the statement formal. Theorem: if say y1t has the Fourier transform capital Y1 omega and y2t has the Fourier transform capital Y2 omega, then y1t into y2t has the Fourier transform 1 by 2 pi y1 convolved with y2 evaluated at, which can be written as follows: minus infinity to plus infinity integrated what you see in the integrand and the element of integration, capital Y1 lambda, capital Y2 omega minus lambda d lambda integrated over all lambda. Now, provided this is of course provided all the Fourier transforms exist, all these transforms exist. We have to keep putting that condition, because we are not always confident that those Fourier transforms would exist, but if they do, essentially we have said that multiplication in the time domain translates to convolution in the Fourier domain, a beautiful second consequence of duality. We will see more in the next session. Thank you.